Hello and welcome to our next topic. We're going to talk a little bit more about the definitions of exponents. We've been working with perfect squares and cubes for a while now. We know that 6 cubed means 6 times 6 times 6, which is 216, and we know that 6 squared means 6 times 6, which is 36. But what about a different power? What about a power of 1? What does that mean? Well, just like there's 3 6s for 6 cubed and 2 6s for 6 squared, there's just 1 6 for 6 to the power of 1. And thus, our first lesson in this part of the unit. A power of 1 just means that thing, either the number or the variable. So anything to the power of 1 is itself. What about a power of 0? That's something that you can sometimes see, and what does it mean? Well, a power of 0 means you're not taking any of those numbers and multiplying it together. So a lot of people would assume that it means it is 0, right? There's no 6s, right? But that's not right. It is 1. So the second rule that we're learning in this section of the unit is anything to the power of 0 is 1. And this can seem strange and a little confusing why, but imagine it this way. Every time you go down in number, say from 3 to 2, here's another way that you can look at it. To get from 216 to 36, you would divide by 6. So if I'm dividing by 6 to get from one step to the next, kind of down the ladder, so to speak, then this should actually kind of make sense. 6 divided by 6 is 1. And therefore, anything to the power of 0, well, it's power of 1, which is just that number divided by itself, and that's 1, because anything divided by itself is 1. There's actually an exception to that rule, which we will get to at another time. But that's kind of the two basic first rules that we learn. Anything to the power of 1 is itself. Anything to the power of 0 is 1. And let's see an expression that kind of mixes these things, because I kind of want to show you something that people get wrong about this type of stuff a lot. So let's see. So here's an expression, 5x to the power of 0, y to the power of 1. So how to read this? What a lot of people do is they assume that this is one part of the expression here, and it's not. So this is what the mistake that people will make. They'll see a power of 0, and so they'll say, this is just 1, and then we have y to the power of 1. So this is like 1y, or just y, right? Yeah? No, it doesn't work that way. This is not true. This is not correct. So why not? Well, I'm going to take that rule with the power of 1, and I'm actually going to go in reverse. Anything to the power of 1 is itself. So if you have just a number, that has a power of 1. So just like we don't say plus 0, we don't say times 1, right? We also don't say a power of 1 usually. Sometimes it just so happens that we do some operation and we end up with a power of 1, but we just don't typically write that, you know? So when I say 5x to the power of 0, y to the power of 1, it's really, it's 5 to the power of 1. And x to the power of 0 and y to the power of 1. Another way of saying this is that every single factor, every single element of this expression has its own exponent. 5 is not connected to this power of 0. This is not true, right? Only x is connected to that power of 0. So what is the real way to simplify this? Well, x to the power of 0, this guy right here, this is 1, that's true, but not 5. This is 5 times 1 times y to the power of 1, which anything to the power of 1 is itself. And so we have 5 times 1 times y, which is 5y. And this is the correct way to simplify this expression. Okay, so watch out for things like that. And we're going to go another step with this. We're going to learn one more rule in this section of the unit. So here we are, we have 5 squared times 5. And I'm just going to rewrite this a little bit. I'm going to color code it a little bit. I'm going to put 5 squared in yellow and 5 in, did I say yellow? 5 squared is going to be in orange, and 5 is going to be in yellow. All right, and so the reason that I'm doing this is I'm going to go to some definitions here. 5 squared just means 5 times 5, and then I'm going to multiply that by one more 5. And so here's our color-coded version of this. But 5 times 5 times 5, that's the same as 5 to the power of 3. And we know that. This is 125. So wait a second here. If I have two different powers, here it's 2 and 1. If I have two different powers and I'm multiplying them together, it seems like I can just take my exponents here and add them together. So let's see if that's true for another combination. Let's try powers of 2. I'll try 2 to the power of 4. Actually, I'm going to go back to my color coding. And I'm going to multiply that by 2 to the power of 3. Okay, sure, why not? So I have 2 to the 4th times 2 to the 3rd. And again, let's color code this. That means 2 times 2 times 2 times 2. That's 2 to the 4th. And I'm going to be multiplying that by 2 to the power of 3. And so when I write it like this, and this is called expanded form, I can see that really I'm just multiplying 7 2's together, but there's another way that I could have got that 7. All I need to do is notice that 4 plus 3 makes 7. And so I can rewrite this as 2 to the power of 7. And since this is just a number, I can actually write this as I can simplify this to a single number. 2 to the 7th is 2, 4, 8, 16, 32, 64, 128, and this is the correct way to simplify it. But you can also do it as two separate things. 2 to the 4th is 2, 4, 8, 16. 2 to the 3rd is 8, and you know what? 16 times 8, that's also 128. So you can do them separately, or you can combine them into one calculation, just 2 to the 7th, and you should get exactly the same answer, which is fine for numbers, but what if we don't have numbers? What if we have variables, which actually are numbers, just that you don't know what that number is yet, right? So let's take this same idea and apply it to an expression with variables. So here we are with x to the 5th times x squared. And again, I'm going to write this in expanded form just to prove why the answer is what it is. And x to the 5th is 5 x's being multiplied together. Here's that multiplication symbol. And then, of course, I have x squared, which is just x times x. But all we got to do is count here. 1, 2, 3, 4, 5, 6, 7 x's being multiplied together, which I could have got by just adding 5 and 2. And so we get to what I'm going to call the product of powers property. And what it states is that when you are multiplying the same base together, you can add the exponents of those bases. So if it's x times x, that's x to the power of 1 times x to the power of 1. Why don't I write that down? Right, x times x, and as we said, anything to the power of 1 is itself, which we are working in reverse here. X, we're turning into x to the power of 1. The other x, we're turning into x to the power of 1. We would just add those together. This is 1 plus 1, and that's 2. And that should make sense. Because this is something times itself, that's x squared, right? So that's the product of powers property. When you're multiplying the same base, you can add the exponents. You got to be careful though, especially when you don't see the exponent. Make sure that you're aware, just because you don't see the exponent doesn't mean it doesn't exist. That exponent is 1 if you can't see it, right? And coming back to this problem here, x to the power of 5 plus times x to the power of 2, that is the same as x to the power of 5 plus 2. And that is x to the power of 7. So this is the product of powers property. Let's do a couple more examples of this, just see it in different contexts. Here is a time where it's inappropriate to use the product of power property, because I have x to the power of 4, but y to the power of 6. So this is kind of like combining like terms with exponent rules, but Not exactly. Don't call it combining like terms. That's not really what it is, but it just reminds me of that because this is a time where you can't use this property because these are different bases. One is x and one is y. So to call this x to the power of 10 or maybe xy to the power of 10, those would both be incorrect. You can't combine these exponents because they have different bases. So this is a time where you cannot use this property, and the best you can do when you can't actually combine things in math is you just kind of write them next to each other. So x to the fourth, y to the sixth, there you go. That's the best we can do. We can't actually add the exponents, so be careful of something like that. Here's another problem where you got to watch out. We got to be very careful. This time we do have the same base, we have x's, but be careful. A lot of times it's easy to think that these are different because one is 2x and the other one is 3x. But actually, a more appropriate way to write this would be to separate everything. The x has nothing to do with the 2. It just happens to be next to it at the time. But these are all different factors. This is 2 times x times x times x times x times 3 times 6 more x's. So everything's being multiplied together. Just because the 2 was written next to the x to the 4th and the 3 was written next to the x to the 6th does not mean that they're, connected more than any other multiplication going on in this problem. So we could actually rewrite this like this, and I think this might be helpful. I might rewrite it something like this if you wanted to use some color coding here. The 2 and the 3, those are still just being multiplied, right? It's not that the 2 is connected to the x's or the 3 is connected to any other x's. They're all just being multiplied. And so multiplication can be done in any order. So why not just say 2 times 3 first, right? And then we can say also we're multiplying the x's, which since they're the same base, this is going to be x to the power of 4 plus 6. And simplifying this, we get 6x to the power of 10. And this is our final answer. And again, be careful, the 6 does not have a power of 10. The 6 has a power of 1. It's just a 6. It's not 10 sixes being multiplied together. So be careful of things like that, okay? And finally, we'll just see one last example. Let's talk strategy with solving these types of problems, or rather simplifying. As we said, this is all just things being multiplied together, and multiplication can be done in any order. And what else you can do is you can multiply just one part of it at a time and then combine everything at the end. So here's what I mean. We have a number, or a coefficient, I should say. We have a variable b, and we have a variable r. And so here's one common strategy when simplifying this type of problem. Multiply the coefficients first. This is 8 times 3, and that's 24. Multiply the variables one at a time. So I have b times b to the third. And remember that if you don't see an exponent, that exponent is 1. Which, using my new product of powers property, I can say that this is b to the power of 1 plus 3, and that's b to the power of 4. Okay, cool. And then same deal with r. I have r to the power of 2, r squared in other words, and r to the power of 5. And if that's true, then I can call this r to the power of 2 plus 5, and that's r to the power of 7, right? So I have found my coefficient, that's going to be 24. I have found the b's, that's b to the power of 4. And I've found my r terms, and that is r to the power of 7. So you see how I can do each part individually and then put it all back together at the end, and I'm done. So that's the product of powers property. Hopefully that makes sense. Thank you for watching, and I will see you again next time. Bye-bye.